All right, what I wanted to do in this video is I know we've already talked about parametric equations and calculus with parametric equations in class, but I didn't actually provide any videos, and I want to go back and I want to just give a little bit of a review, kind of a succinct overview of all the stuff that we've done so far in 10.1 and 10.2. Okay, so 10.1 and 10.2 are all about what are called parametric curves. In class, we talked about why we would want to do this, but there's good reasons why sometimes parametric curves are a little more natural to use rather than the usual curves. And what I mean by parametric curves, we're still going to talk about points in the plane as points x, y. But we're thinking of x and y not as functions of each other, but as functions of some other common parameter t, hence parametric equations. So typically we think of x as a function of t and y as a function of t, and they can be functions of t independent of one another. They don't necessarily have anything to do with each other. So the example that we talked about in class was when, so we took a car and we took the car and we drove it off a building, and the x coordinate turned out to be just linear. And the y coordinate, we had to account for gravity. And here the x and the y directions are in a certain sense independent, right? The x is just linear. It's just going to be some constant depending on the speed of the car. And then the y is going to depend on gravity and the usual formulas there. So the 1/2 at squared plus v naught t plus s naught, right? The usual motions when you have constant acceleration. So anyway, so there was a scenario where the x value and the y value were independent, and therefore it made sense to think of x as a function of t and y as a function of t, not necessarily them as being functions of each other. Okay, so this is the kind of thing that we're going to do here. And so what I want to do is I want to just work with a few examples. So the main way that we can kind of get a hold of these parametric curves, at least at first, until they become and feel a little bit more natural, is to do what's called eliminating the parameter. And what that means is that we're going to take the parametric equations that we have and then try and write them non-parametrically. So for example, if we were to have x is 2t minus 1 and y is 4t squared, it's not clear right away what curve this is going to look like. But what we can do is we can take this equation and solve for x in the top equation, and solve for t, and t is going to be x plus 1 over 2. And so if we take that value and plug that into the bottom equation, that leads to y being 4 times x plus 1 over 2 squared, which is just x plus 1 over, just x plus 1 squared. Okay, the 1/4 in the denominator and the 4 out front cancel. And so this is just the normal parabola y equals x plus 1 squared. So that's going to look like a parabola. It's going to have a base at -1, 0. The other thing that's different, that was a terrible parabola. The other thing that's different here is that for parametric curves, these curves also have a direction. And so for our case, our direction is going to go from left to right. And the reason for that is that the x coordinate is, so if you look at this curve, I mean, you could do it just by plugging in different values. So for example, at t equals 0, you would look at x is -1 and y is 0. And if t is equal to 1, then you get x is 2 times 1 minus 1 is 1, and y is 4. So you get the point 1, 4. And so here, those curves are going in that direction. So that's how we know that curve faces that direction or traverses in that direction. And if you were to have, if this was to be a curve that were to face in the other direction, then that doesn't actually change what the curve itself is. It just changes its direction. And that can have an effect when we talk about area and when we talk about surface area. And that's going to happen when we introduce calculus into these parametric curves. Okay, so that's the kind of brief overview here. Most of the time you can just do the substitution method. So here we just solved for t in one equation and plugged it into the other. The only other real trick that I can think of is where you have something like x equals, just say x equals 4 cosine of t and y is 3 sine of t. And here, what you can do is instead of eliminating the parameter, it's easier just to look at x over 4 squared plus y over 3 squared. Okay, and it turns out that that's going to add up to be 1, because we know cosine squared plus sine squared is 1. And if that adds up to 1, then yeah, so x over 4 squared plus y over 3 squared is going to be 1. This is going to turn out to be an ellipse. Okay, so that's how that's going to work. That's really, those are kind of the two big scenarios. There's a few other cases, but most of the time we can get away with substitution or thinking about sine squared plus cosine squared being 1. So with that being said, that's basically everything I wanted to talk about as far as an introduction to parametric equations. And what I want to do now is I want to just turn to this example that we're looking at, where x is 2t minus 1, y is 4t squared. And then I want to do calculus with that curve. So we know it's a parabola. We know everything's going to work out more or less pretty nicely. But what I want to do is I want to talk about the following. So let's again look at x is 2t minus 1, y is 4t squared. The first thing we should talk about is, how do we find the derivative? How do we talk about the rate of change of y with respect to x? And it turns out that the way that we're going to have to do this is with the chain rule. So we get, this is dy dt divided by dx dt. Dy dt is just 8t, dx dt is 2. And so it turns out that dy dx as a function of t is going to be 4t. And then if you plug in a particular value of t, you could figure out what the point is that you have, and then plugging in the value of t here would tell you what the slope of the tangent line at that point is, right? It's the derivative. And then we can also do things like finding the second derivative. So remember that the second derivative is just the derivative of the first derivative. And I write it like this because I think it's important to think about if I were to take this derivative, d over dx of dy dx, this is going to be a derivative with respect to t of dy dx divided by dx dt. Just kind of following the same pattern as before, that kind of chain rule. And the derivative of dy dx with respect to t, well, dy dx is 4t. So if we differentiate with respect to t, we get 4. Dx dt, x is just 2t minus 1. So dx dt is just 2. And we end up with 2. And that's consistent. Remember, we had already eliminated the parameter. That's consistent with the fact that if y is x plus 1 squared, then we know that, so this is x squared plus 2x plus 1. We know that y prime, or dy dx, would be 2x plus 2. And if you compute 2x plus 2, guess what you get? You get 4t. And if you take the second derivative, that's just 2, right? So again, that's also consistent. So everything here is consistent with itself, but that's how we find derivatives. We can also talk about areas. So if we're going to talk about the area that we get on a parametric curve, we're going to find the area from one time to another. So from one value of t to another. So for example, if I wanted to find the area of this curve again, okay, so 2t minus 1 for x and y is 4t squared. If I wanted to find that area, say from, so the area under the curve, x is 2t minus 1, y is 4t squared. From, say, t equals 1/2 to t equals 1, that's going to be given by the integral from 1/2 to 1 of y dx. And the way that we interpret that is our y is 4t squared. And by dx, what we mean is x prime of t dt. And the derivative of x is 2. Okay, so our dx here is just x prime of t dt. And that's what we got there. Okay, and so this is going to turn out to be, I'll save you the suspense, but this is going to turn out to be 7/3. Okay, so you can go through, and that's a Calc 1 integral at this point. You can do that very quickly. So that's the area under the curve. The only caveat I have to mention is that, remember, we talked about the direction of the curve before. The direction can actually make the area integral negative, but area, of course, is positive. So you can either put an absolute value up front or put a plus or minus in front, and just always take the positive value that you get. So as long as you didn't make a mistake in the calculation, you can just change the sign and make it positive. Or if you like, you can change the bounds. That's the way that the book likes to do it. Okay, but the area is always going to be positive, of course, being area. We could also talk about things like arc length. So for the arc length of a curve from one point to another, this integral here is just going to be, so from one time, so from t1 to t2, And we're going to have the square root of 1 plus the derivative squared dx. And if you write out what dy dx is using the chain rule and simplify, it turns out that this is the integral from t1 to t2 of dx dt squared plus dy dt squared dt. So that's the arc length formula. This integral is always going to be positive because square roots are positive, right? We know that y equals square root of x is always it's the positive or the principal square root. So we never have to worry about the sign problem with arc length. And then the final thing to talk about is the surface area. So if I want to talk about the surface area of the surface of rotation obtained by rotating this parametric curve about some given axis, the surface area is going to end up being the same formula as before. So 2 pi y times the surface area formula that you're going to get. So dx dt squared plus dy dt squared. Okay, and this this formula also is going to have a potential to be negative because maybe y is a negative function over this given time period, or yeah, maybe x is decreasing. So this is really, this dt came about because you had an integral with dx and then we simplified just like what happened before. And at any rate, it's possible that this integral is also going to be negative. And so you can do the same trick as with the area. You can just change the sign so that your surface area is always positive. Okay, and that's really everything that we did in 10.1 and 10.2 kind of boiled down to these few examples. Okay, so that's really all the material that we covered in those first two sections.